Okay, then we'll start talking a little bit about sound. And so to define sound depends a little bit on whether you're actually really talking about physics or physiology or psychology. So from the physics point of view, what we will typically call sound is the whole process where some system creates some sound waves, disturbance. And so sound waves are essentially traveling waves that transfer energy, longitudinal waves. And we will describe those waves and how that works. And sound waves are then essentially picked up by our ear. Now, if you define sound in terms of physiology and psychology, it's about kind of hearing that sound wave, kind of detecting the sound waves, but also the perception of that sound. And there's a lot of things that are going on there, both in your ear and in your brain, that can turn very complex sound waves into individual patterns that we can actually recognize quite easily. So there's a lot that you could talk about in terms of sound, both from the physics side and from the physiology side. We're not going to cover everything here. There are just a few things that we wanted to highlight. And so it's important to realize that waves transport essentially energy, right? And so when we talk about intensity, and intensity is something for sound that you've heard typically expressed in a unit called decibel, for instance. What that really is a measure for that energy that's being transported by that wave. Now, if you've looked at the unit for simple harmonic motion, you've seen that the energy in simple harmonic motion is 1/2 times Ka square, where A is the amplitude. And so if you have a wave where you double the amplitude, you will actually quadruple the energy that's contained in that simple harmonic motion. But now when we're talking about a wave, we're not just having this simple harmonic motion, this displacement going up and down. It's also the case that you have a traveling wave, right? And so the frequency also plays a role. The faster you actually transport that wave, the more energy you need. And so for a wave, the energy is also proportional to the frequency. And so whether you double the frequency or you double the amplitude, it doesn't matter. Both of those operations will actually quadruple the sound intensity. If you would double both the frequency and the amplitude, you will actually increase the intensity by a factor of 8. So it's very easy to increase the intensity of sound. And so the intensity really is a measure for energy. And so we quantified it a little bit more by describing it in terms of the power of a sound. And so the power is the amount of energy per unit of time, but also now per unit area. And so if you have right here at the center, say a point source, say a small speaker that essentially broadcasts some sound, that sound will actually spread out in like a spherical way. And so the energy gets distributed as you go further away, the energy gets distributed over larger and larger surface area of that sphere. And so that means that the intensity will actually go down because the same amount of energy that's being broadcast from that little point is being spread out over a much, much larger area. And so that intensity actually follows what we call an inverse square law. So if you double the distance, the intensity actually will go down by a factor of 4. Okay, and so one of the factors that will determine the intensity of a sound is actually the distance to that source. So being further away from, say, speakers at a concert definitely will be better for your ears because the intensity drops off by an inverse square law. Then let's talk about the human ear, and we have an expert in our physiology here in the house, Dr. Wong.
By no means I'm an expert, but I did hear Dr. Brian Allman's talk from the anatomy and cell biology here at Western. And so I like to see if I can uh, condense it to a few slides for you. Um, and the human ears can hear a range of frequencies like what we discussed last time, but also a very wide range of sound intensities. Um, Dr. Cami, can you advance the slide? Yeah, thank you. So it's very interesting that we use this 1 kilohertz as the reference, and your ear cannot hear. If we speak softer and softer, you won't be able to hear us. And at that 1 kilohertz frequency, the sound intensity that we can begin to hear or begin not to hear is 10 to the minus 12 watt per meter square. And our ear can tolerate sound up to 1 watt per meter square. So those are the huge range of intensity that our ear can handle. So that's so because that over 10 to the 12, so that's why we use decibels, and decibels it's log of the intensity divided by the intensity that we reference to, which is our reference of hearing. And we multiply by 10 to make the numbers easier to communicate. So I think, yeah, go ahead. Next slide. I think we can pass this slide. The slide after this has a list of numbers. So threshold hearing, like we said was 10 to the minus 12 watt per meter square. And jet airplane is 10 to the, it is 140 decibels. Oh, I see that that's bursting of eardrums at the very end is 160 decibels. So, and that's in between. Rock concert, I guess that's what Professor Cami like to hear things at. It's at 120 decibels, I guess. Okay, maybe the next slide, please. So we talk about the loudness of sound, but not the frequency. And what I like to focus in on is actually the human ear. After coming through the eardrum, it get connected, the sound get connected to this cochlea. And I like to just talk about how it handles listening to the different frequency. Could you advance the next number of points on the slide? Yeah, so it's very interesting that if you unwind this cochlea, there's a basilar membrane in it. And this membrane actually has hair sticking out, and below the hair is nerve connected to them. But this basilar membrane is very weird in the sense that it has certain different thicknesses and at different tension, different stiffness. So at different parts of the basilar membrane, over here versus over there, it would respond to very different frequencies. And the way it does that is this. I don't know if I'm hoping you know this equation. V is the frequency of the wave times the wavelength of the wave. So that's how fast the wave is traveling. And a lot of times, not a lot of time, it is always true that the speed of sound propagation in the medium is set by the medium. So for example, speed of sound is set in air, and speed of sound will be different in a solid material, but any material that would determine the speed and speed of wave propagation. So for example, speed of wave on a string, that speed would be set by, say, the tension of the string divided by the linear mass density of the string. So basically, how much tension it is in the string and how heavy the string is. In air, then it could be what we call the bulk modulus and divided by the air density. So the bulk modulus kind of like you can think of it as like the tension is the restoring force, and the density corresponds to how much inertia there is, how much mass there is. So phi is basically fixed when you give a given medium. And then you can look at the frequency. Sorry, not the frequency, the wavelength. The wavelengths will be set by the boundary condition. So lambda, it could be either if it is fixed ends. So if two ends are fixed, your frequency, your wavelength, this could be half a wavelength here. So this is fixed end. So fixed end, fixed end. And then there are open end condition too, but let's just do it one at a time. And so this would, if you have fixed end, you could have that wavelength, or you can have one wavelength that's fixed in terms of that. So if the fixed distance is L, lambda here would be 2L. Lambda here would be 2L, and then you can keep drawing the higher and higher frequency if you like. So now the wavelength is set by the boundary condition. Then the frequency is kind of set. It's determined how it's the free floating parameter that has to satisfy that equation. So the frequency. So I'm going to write the frequency to be phi. Let me color code it. So frequency is phi over lambda. So what happened is that if you unwind the base layer material, it's very interesting. Our ear is made it so that on this side, this end on one end is thick. So this side is very thick, which translates to mu, the linear density being high. So high linear density. And not just thick, but it's also loose, very loose. So that the tension is low tension. And as a consequence, the fundamental frequency, or the lowest, the frequency that it vibrates in, which is now set by phi over lambda, is low. So phi, so when it's thick, that means the phi is low. The speed of propagation is low. Speed of propagation low, and then it's loose. Sorry, let me say that one more time. The speed of propagation is given by square root of the tension divided by the linear mass density. So when you have low tension and large mu, then phi is low. So when phi is low, then F is also low. So this frequency that it responds to, it vibrates at, is low, and in our human ear is around 20 hertz. On the other hand, this side is very thin, and it's gradually changing. So this side is thin, and it's held more tightly. And so then phi is high, the speed of propagation is high, and the frequency that it would respond to is phi over lambda again, would be high. So frequency is phi over lambda, and so this would be high frequency. High frequency, so which would respond at 20 kilohertz. So depending on what frequency comes into the ear, if it is say at 20 kilohertz, high frequency, this part of the membrane would vibrate at 20 kilohertz. And this part of the membrane vibrates, it will then wiggle the hair. When the hair wiggle, then the nerve ending will be sent to the brain for that particular location. And then if it is 20 hertz, this part of the membrane will vibrate, and that part of the hair will vibrate, and the nerve ending will send a signal to the brain. So all the signal gets sent to the brain at different parts of the basilar membrane, depending on what frequency it gets excited at. And so I don't know if you guys are appreciative of how we can hear different frequencies. But now I hope that you'll have a even better appreciation of how lucky we are to be able to listen to different frequencies or all at the same time.
It's pretty impressive, both the range in frequencies and the range in intensities that we can hear, right?
Yes, yes. Okay, I pass the yeah, I'll pass this back to you. I think that.
Okay, you wanted to say something about this, or?
Oh well, I don't know if students are interested. They have, sometimes the certain parts of the membrane or hair, actually it's the hair loss that as one age, that causes certain part of the hearing to be gone for a certain range of frequency. So we have these cochlear implants that can excite the nerve in the part that where it needs to be. So there's a device outside that collect the sound, and then it get implanted inside. I don't know if you can see, there's a wire in here that goes all along the cochlea, and it will stimulate the different parts of the basilar membrane as a function of the frequency. So that's how a cochlear implant works.
Great, thanks.
Yeah.
Okay, so if there's any questions, then not immediately. So then let's try to connect a bit more what we've talked about in terms of waves to actual sound. And so we've talked already a little bit about frequency, and so frequency is one of the things that we can hear. There's few other things that our ear can actually distinguish more than frequency and intensity. So for intensity, we just talked about this decibel scale, which is a logarithmic scale. So we hear sound in a logarithmic fashion, but it's actually the same when we listen to frequencies or pitch in the instrument. So what we hear as 1 octave higher is actually a factor of 2 in frequency. And so what it means is that what you perceive to be a linear increase in pitch is actually a logarithmic increase in frequency. Okay, and so that's kind of important to keep in mind when we discuss some of the frequencies in a bit. So I wanted to give you a little bit of an idea of what a waveform actually does to sound as well. And so when we talked about simple harmonic motion, or we talked about waves, we've talked about these sine waves, and like how realistic is it actually that a sound will take the shape of a sine wave? Well, we can actually visualize that. And so how does this really work? And this is now pulling a few things actually together, right? So we're going to describe a wave. What is a wave? Well, it's essentially some disturbance that is traveling through space. And what we do when we build a speaker, for instance, is we make a speaker vibrate, right? And we've seen it last time, the students that made this project, the vibrating paper plate, that essentially is a speaker. So it pushes air molecules, compresses them, and that wave will actually then propagate and reach our ears. But how we make it propagate, how we make this speaker vibrate, we can actually choose. And so, for instance, we could take a sine wave to actually drive these oscillations. So we can actually change the position of the speaker in such a way that at each moment, the position of that speaker actually follows a sine wave. And if you do that, then of course, the sound wave that will be generated will also have changes in density and pressure that actually follow this sinusoidal pattern. And that also means that when it arrives at your ear, that's what you'll hear. And so what I've done is I've actually created sound waves based on these patterns. So in this case, this is a sine wave, and I've made it a 400 hertz sine wave. So you can actually calculate as a function of time how many amplitudes or how many wavelengths you actually should have. And so a sine wave of 400 hertz sounds like this. Okay. Now, with your ear, you can hear frequency. So if we do the same sine wave, but we double the frequency. Okay, let's double it again. Okay, so that's one thing. That's a sine wave. It's kind of a boring beep. Let's hear it again. Okay, what if we actually change the shape of that waveform, right? So what if instead of a sine wave, we actually turn it into like this triangular shape, right? And so again, this represents the displacement of the speaker cone as a function of time, for instance, right? So this looks like a fairly small change. We go from something which is a sine wave to something which is a triangular wave. Would our ears actually hear that difference? Okay, so let's see if we can actually hear that difference. Sine wave. Triangular wave definitely sounds a bit more sharper. Okay, let's change it up a bit more. Here's a sawtooth wave. Blaring. Square wave, it's still a different shape. And then here's a bit of a combination. It's a sine wave and a triangular wave and a square wave that I've combined. So they're all at 400 hertz, so they're all at the same frequency. The only thing that you hear differently is that waveform. Okay, and so this has a little bit of the character of all these different tones that you heard. And so in principle, you can turn anything into sound. And as an example, so what I did a few years ago is I took the midterm histogram of the class that year. And as you see that histogram here, and I actually turned that into a sound wave. So essentially, I was going to repeat this precise pattern 400 times per second to make it 400 hertz. And so actually this histogram in the same representation as I had before looks like this. And so if you turn that to sound, that's how a midterm histogram sounds, right? Yeah, you can. I had the contest back then to name that sound, but I didn't get very clear winners. So far, the sounds have really been a little bit boring, right? It's just like a single sine wave, something like that. What really becomes is interesting is if we actually add different frequencies of the same tone. So let's again listen to the sine wave. We had the 400 hertz. This is the 800 hertz. Okay, what if we actually combine them? So now this is a combination of the 400 hertz tone and the 800 hertz tone and the 1600 hertz tone. So it's the same sine waves. It's just that we've added them up at the same time. And I did actually change the amplitudes a little bit. But now you start getting more interesting sounds. So now you kind of, with a bit of imagination, you kind of get closer to what could be an organ sound, for instance. Right, and here's a different way, just a different scaling. It's the same waves. It's just I've changed the amplitudes a little bit of the individual components. Or this one. Okay, and so you can now start thinking, hey, you could go playing with all these different waveforms and create your own sound. And so essentially in a synthesizer, this is one of the things that can happen. You can actually generate the waveform. Of course, in real instruments, there's other things that play a factor as well. It's not just the frequency. You will have other characteristics that are typically called attack and decay and sustain time. So how you actually change the overall amplitude, which then will determine how loud something sounds. That also determines the timbre for musical instruments. Okay, so that's now how these waveforms will determine the sound. What else can we do in terms of, say, physics of waves and sound? Well, so if you go over the material on OWL, what you'll see is we actually describe the wave equation. And so the wave equation can be derived from essentially considering what happens to a piece of string on a wave. We write down the equation of motion. And so that equation describes how waves can travel on strings. Now, in a bit, we're going to apply things to strings on a guitar and the waves that can actually travel on that guitar string. Now, a guitar string, actually, let's maybe get a guitar out. So a guitar string is not a completely free string, right? It's clamped on one end. So that means that here the string cannot really move, but it's also clamped on the other hand right here. So there a string cannot move either. So that means that it's not just a traveling wave on a string. Essentially, it reaches a boundary on both sides. And so now the question is, what is going to happen to a traveling wave when it hits a boundary? And so what happens is that you get reflection, and the sort of reflection that you get for a wave, that really depends on the precise boundary conditions that you have. And so look on the right-hand side, for instance. So if you have an open end, so for instance, you have a piece of rope with a ring around the pole. As this wave comes to the end here, it will actually lift the ring up, in an uninhibited way, and that will fall back down, and that's like actually a hand yanking back down to create another pulse. And so what you get is a reflected pulse in the same the same amplitude, but in the opposite direction as the incoming wave. And so at a loose end, you essentially, an open end, you essentially just reflect the wave. But what if the end of your string is actually attached to a wall, for instance, or something else which is solid? So this is now a clamped endpoint. So now as this pulse of this wave actually approaches the wall, it's actually pulling upwards on the wall, but that's a fixed point. And so Newton's third law tells you action is reaction. So this wall is actually pushing back or pulling back on that rope. It's pulling it down. And so that pulling down on the rope generates this inverted wave here, okay? And so for a moment they overlap and they essentially completely cancel out, but then a bit later you actually see that this reflected pulse is emerging. And so what you get if you have clamped ends is that each time your wave reaches one of these clamped ends, it will reflect, but it will essentially be inverted. And so clamped essentially means that that point is fixed, that point cannot move up and down, right? So in the case of this ring, for instance, this ring can move up and down, so that's not going to stop that wave. Okay, and so that's very different whether you have an open end or a clamped end. That will actually determine what will happen to your reflected wave. And so if you have strings with ends, which of course you always really have, you always have reflected waves. There's no way around that, right? And that's kind of key to remember when you talk about instruments. So if you would like to play with it, there's actually a very cool simulation where you can play with waves on a string, either pulses or continuous waves with open or clamped ends. You can change the frequency, you can change the amplitude, and you can actually see what happens on the spot. Now, the reason why this is important is let's now really zoom in on a string where both ends of the string are clamped. So this leads now to what's known as standing waves. And so if you look at this figure here, what you see is a green wave, which is traveling to the right at a constant velocity. And then you see a red wave, which is traveling to the left. Both waves have the same amplitude, they have the same wavelength, they just travel in opposite directions. Okay, so you could think of it as a wave traveling to the right and then being reflected essentially back. The blue is what you get if at each moment in time you actually add up both waves. And what you see is something that still looks like a wave, it's just that it's not traveling anymore. What you now get is that at each of these points here, you get simple harmonic motion, either with a high amplitude or places like here, essentially with no motion whatsoever. These are now standing waves. And at the end point, so at the beginning and the end of the string, if you look, they're clamped because they're always at the same position. And of course, it's not quite the same on the inside of the string. And so you can work out that this is given in one of the lessons on OWL. Actually, you can work out that this is essentially the expression that you get for standing waves. And so let's now plug in what it means that these boundary conditions here must be met, so that at position 0 our string is not moving, never in time, and also at the other end our string is not moving. So let's plug in x equals 0. Well, you plug it in here. The sign of 0 is 0. So great. We have no up and down motion at the 0 point. So that's always great. What about the other end? So if we have a string which has a length L, right, then what it means that we need to implement this boundary condition is for x equals L. So at the position of the length of our string, this expression needs to be 0. So that means that the sign of KL must be 0. And that can only happen if k is pi over L or 2 pi over L, or in general n pi over L, with n an integer number. Okay, so that means that not all waves are possible. Only waves with wave numbers corresponding to n pi over L, where L is the length of your string, those are possible. That has important implications, right? Because so that's now our condition for our standing waves for our string. But we also know that it holds for any wave that that wave number k is related to the wavelength. It's 2 pi over lambda. And so if we equate these two sides, you actually find that now the wavelength of your waves that can actually travel on your string, those wavelengths are restricted. Only waves that have a wavelength which is 2L over n, with n an integer number, are waves that can actually exist on your string. And so if we make n equals 1, then the wavelength is actually 2L. So that's the longest wavelength that we can have. Now, if this is the length of the string here, a wavelength of 2L is essentially a wave that goes down up here and then down here, right? So you need to have the full up and down motion to have a full wavelength. And so this wave with this wavelength, okay, that essentially is the longest wavelength you can have, or the lowest frequency tone you can actually make on a string. A second solution would be for n equals 2. Now your wavelength is actually the length of the string. So this is L equals 2. And so what you get now is that both ends are not moving, but also in the center, there is now what's called a node point. And so a node point is essentially a point that is not having any displacement in these standing waves. The antinodes, on the other hand, are places where you have like maximum amplitude in the wave. So for the n equals 1 case, you will have the maximum amplitude right here at the center. So that's an antinode. In the case of n equals 1, you actually have two antinodes, and they're right here. And so you can just continue, make n larger, and each time you'll see that you can make waves with shorter and shorter wavelengths. But you cannot make waves on a string with wavelengths anywhere in between that. Okay, and so if you have a limited length of string, then essentially, you know, there's not just anything that you can do. There is a limit to the number of waves that you can actually make on the string. And so they have names. This is called the fundamental mode, okay, and that's essentially, it corresponds to just plucking a guitar string without touching anything else. That's your fundamental mode, also called the first harmonic. And yeah, so sometimes the nomenclature can get a little bit confusing. This would be the second harmonic, but it's also called the first overtone sometimes, because it's not the fundamental, it's the overtone, and so on. But so in all cases, what you have is you can make your wavelength smaller. You have some of these node points that are not moving, and then you have some of these antinodes where the motions are largest. Okay, you can have something similar. This is now a transverse wave. So guitar string is a great example of a transverse standing wave like that. But this can also be the case for open tubes, where essentially you have standing waves like this, for instance, in organ pipes. So, okay, one more thing to do to actually kind of get things together. So we can now express the frequency of our standing waves in terms of the fundamental properties of the string. And that's kind of where we start pulling things together. So we've seen before that the frequency is given by omega over 2 pi, and omega is essentially something which is determined by the physical properties of your system. And so in particular, we have seen that for a wave of a string, the velocity is given by omega over k. But we've also seen that the velocity for a wave on a string is a square root of t over mu, as Dr. Wong just actually repeated. And so from that, if you just plug that in here, you can, oh, and yeah, so we know now that the wavelength for our clamped waves on a string is 2L over n. You actually get an expression for what the frequency is that you can get from that string. And so let's now actually put n equals 1. Let's just look at some of these fundamental frequencies. And that actually gives some insight if you can actually use a guitar. And so here's the first question that I have. So when you look at these solutions for a string, you have a fundamental, you have overtones, you have all these different solutions to the wave equations for the strings with two clamped ends. It's not any possibility, but there are different allowed solutions. So if you pluck a string, how does your string actually know whether it should produce the fundamental mode or the overtones? Anybody have some idea how your guitar would know that? Right, and so just to clarify, let's go back maybe here. So if you pluck a string, how does your guitar know whether it should be vibrating like this wave at the top here, or perhaps rather this wave at the bottom? How does your guitar know which vibration it should go into? Yes, Hamza.
Is it perhaps through tension? Like,
yeah, tension will certainly have something to do with it.
Mm-hmm.
But there is a little bit more to it. If you put your finger at the middle of the string, that's actually an excellent point, right? So if you put your finger in the middle of the string to pluck it, right, then you're actually forcing your string to essentially have a large amplitude right here at the middle, okay? So that means that this second harmonic here is not going to be possible, because the second harmonic is a mode where this actually needs to be standing still. And so these harmonics are things you can actually get on guitar as well. So let's see if I can demonstrate it here. So if, let's see, just about see the guitar. So this is my entire guitar string length. This is the halfway point of my guitar. So this is half the string length. Actually, Mariam, can you perhaps spotlight the video for a minute? I don't actually know if that's really possible right now. But so if I pluck my guitar string here, what I'm going to do is I'm going to really tell the string like, hey, I want you to have a large amplitude right here where I pluck it. So that's going to activate the fundamental mode. And so that's a fairly low frequency. If I want that second harmonic to be excited, I want this part actually to not move at all. This should be still. And so the way that I can actually try that is I can lightly put my finger on here and plug the string again. And so you hear a sound, which is different. It's actually higher than this sound. It's actually twice the frequency, because now this point is not vibrating and you have maximum vibration here. And so halfway on your strings, you have these sounds. These are called the guitar harmonics. And so what this means is you just make sure that there's no motion of your string right here at the halfway point. So that's what a guitar sounds if there's no fundamental sounding, and there's more here. Oops. They get harder as you get closer to your fret. So each time what I do is I actually say like this should be a note point, and that's where there should be no string motion. Okay, and so back to the question now. So how does your string know whether to produce this fundamental tone or the overtones? Well, part of it is going to be how you pluck your guitar string, but in fact, many modes are produced at the same time, right? Depending a little bit on how you play. As you see, you can actually really pick some places that will prohibit certain sounds from happening, or certain frequencies from happening. But essentially what you normally, when you play a guitar, what you will hear is you will hear essentially a combination of these fundamental and several overtones. And depending on playing technique, you can actually enhance that, and you can actually really hear that, because you hear the difference between those different modes. And so on an acoustic guitar, that's often demonstrated by a difference in what's called tasto and ponticello technique. So if you pluck your strings over the fretboard, essentially what you do, right? So if you plug your strings right here over the fretboard, what you do is you activate these fundamental modes. And so that means that the higher harmonics are going to be a lot weaker, because essentially the higher harmonics need to be still at those points. And so it's called tasto, and it's typically a fairly sweet sort of sound. Whereas if you pluck your guitar strings here at the back, what you're actually allowing to happen is you can actually activate a lot more of these overtones. And so you get much stronger harmonics. You actually see in this diagram here is what's called a frequency spectrum. So it's telling you what sort of frequencies are participating in sound. And so if you play it over your fretboard here, you get a lot of these lower frequency tones, but not a lot of high frequency tones. Whereas if you play it at near the bridge here, you get a lot more of these high frequency tones because those can now be activated. And so that sounds much more, you know, nasal, sharper sound. So it's this sound versus this sound. I think you really hear that difference, right? And so you can use that in as a style. Right, so you very clearly hear a difference in how that guitar sounds, right? And so that's just a difference in fundamentals versus higher harmonic. So now let's look a little bit more in detail to a few other things. So when we look at a guitar, we have essentially 6 strings, okay? And so all these strings have essentially the same length and that they have available to produce standing waves. And now how can you actually create different frequencies? And I think for this, I'm actually going to move over to my, what I call my acoustic physics lab. Okay, so let's take an electric guitar, because why not? Okay, so we have 6 strings in our guitar, and they have the same length L available to produce all these standing waves. So now, how can we actually create different frequencies? Okay, so there's a few different ways to do this. So let's first look at the very basics. So this is our equation that we have for the frequency of our tone given the length and the tension and the mass density of the guitar. So if you increase the tension, yes, you will get a higher pitch, right? If the T goes up, the frequency goes up, so higher frequency will be a higher pitch. Lower mass density, right? If mu is lower, you will get a higher pitch. If the length is shorter, you get a higher pitch, okay? And so let's first put this a little bit to the test here, okay? So our low E, this tone, this tone here, okay, that's a frequency of 82.4 hertz. Now this high E, so I'm actually playing the lowest and the highest string, okay? So the lowest E has a frequency of 82.4 hertz. The high E has a frequency of 329.6 hertz, and that's a factor of 4 in frequency, okay? So how do you actually get a factor of 4 frequency difference between strings of the same length? Well, so the length is the same, so it's going to be either the tension or it's going to be the density, right? Now, a factor of 4 in frequency means essentially a factor of 16 in the tension or a factor of 16 in the density, okay? And so that's actually pretty hard to do in tension, right? What you want when you play guitar is you want your strings to be roughly the same tension. Otherwise, it's very uneasy to play, right? One string you would have to pluck very hard, and the other you would have to pluck only lightly to get a sound out. So that's why you want the tension to be roughly the same. So for guitar strings, yes, you have to actually go for density. And so yes, a factor of 4 in frequency is indeed 2 octaves. Okay. And so here's the spec sheet for a set of strings. And so what you see here is you go from the low frequency 82.4 hertz to the high frequency 329 hertz. And so these are the string masses per unit length. So these are the densities, and these are the tensions given in kilograms here instead of Newton. And so as you see, there is a difference in the tension, okay, but they're all around, say, in the 7 to 9 kilogram range. So not too dissimilar. But look at this range in densities, okay? So you go from a density of 6.8 times 10 to the minus 3 to 0.4 times 10 to the minus 3. And so that actually is a factor of 17 in density. And so that's one thing, that you just have the different, thinner strings do break more easily. Now you can actually change the tension in your strings, and you typically you have to do that sometimes when you're actually tuning your guitar, right? And I actually need to grab something else. So let me actually stop sharing here for a second. Okay, so when you turn these keys right here, you essentially also change the tension in your strings. And so if I plug this string and I lower the tension, the sound goes down, right? So if you increase the tension too much, of course, what's going to happen is you're going to break your string. Okay. The other thing that I want to mention while we're about tuning the guitar, there's also this concept of beats. If you have frequencies that are very close together, what you start to hear is you start hearing beats, which is modulations in the amplitude of your tone for frequencies that are really close together. And so that's one thing that you can use for tuning. If I press this string here and I play the other string, they should have exactly the same frequency. If you hear this wow, wow, wow sound, right? So that tells me that they're not perfectly tuned. That's better, right? And so again, that is something that you do by changing the tension in your string. Okay, so let's go back to this. Okay, guitar harmonics I've essentially just talked about. You can do that, of course, on an electric guitar as well. But there's other things you can actually do to change the pitch, right? So we talked about difference in the density. Now let's actually see there's two things left in changing the frequency of a string, changing the length, and changing the tension, okay? So let's have a look at those things now. And so to change the length of the string, you can actually press down. Right? If you press down these strings, what you do is you change the length of your string. You change where the clamp is on your string ends. And so that's kind of an obvious way to actually shorten your string. But you don't necessarily have to use the frets for that. You can also use something like this. This is a bottleneck. Now you can continuously change the clamped end of your string. Okay, that's another possibility. And then finally, the other thing that you can do, and that's more of a technique thing, is you can actually bend your strings. And so bending your strings will increase the tension, and so that will increase the pitch. And as you see, it doesn't matter which way I bend, whether I bend up or I bend down. What I'm essentially doing is I'm pulling my string up or down, but in both cases, it's actually increasing the tension, so it's increasing the frequency. And so you can do that technically in two different ways. You can start on a certain tone and then bend up. like that, or you can start from the bend up and then come down, or have two at the same time. And so that sort of bending is something which is actually widely used. For instance, in blues. Let's maybe do a little backing track on the blues. Okay, so if you're a blues fan, this is what you like. I'm just wondering whether are there people in the audience that are more like rock fans rather than blues? Okay, yeah, so this is also used in rock. Let's maybe do a rock example, but I need to use my rock guitar for that one. So this guitar is a different guitar than the other one, and what's kind of special about it is that the guy that designed it actually knew his physics. What he was saying is like right at this point is one of the locations where some of your lower frequency sounds would actually have the highest amplitude. So this is where my other guitar actually has two more frets. But here essentially is like, no, this is where you won't have this pickup, because if you have your pickup there, you'll actually pick up those low tones, and that's kind of a nice rock sound, especially if you put a little bit of overdrive on your guitar. Okay, and now combining that with the bends and some rock and roll, perhaps. There you go, rock fans. So you can also bend the strings when you're doing rock and roll. Oops, kind of lost my pointer here. Okay, so now for the last part here, with the wiggling the fingers near the top. Oh, that's a vibrato actually. If you do this, what you essentially do is you constantly change the tension of your string up and down, and so that causes this vibrato. Right? But now okay, I'm losing something here. Just a second. Okay, let's go back to this for a minute. Okay, so now let's go over the physics of electric guitar specifically. And so you may think if you look at the guitar that what's underneath the strings are small microphones, but that's actually not the case. And so this is now where we go back to talking about magnetic induction. Okay, so these pickups right here under the strings, these are essentially small little magnets. Okay, as you see here, there's magnets sticking out underneath each of your string. There is a little magnet sticking out. Why would you do that? Well, it turns out that if you make sure that your magnets are made of the right material, you can actually magnetize your guitar strings. And so your magnet will create a magnetic guitar string. And if you then pluck your string, you now have a moving magnet, right? Your guitar string has become a magnet. And you have a moving magnet above your pickup element. And you see around your pickup element here, you have a coil. Okay, and so now you have your moving string, which essentially is a moving magnet over a coil. So you'll actually generate a difference in magnetic flux in that coil. That means you generate an induced flux, and that's the signal that you then actually amplify in an amplifier. And so that's why actually you cannot just choose any material to make your strings, right? Suppose that you would have this James Bond type movie where you know, you would have our Goldfinger has essentially golden empire and also has a gold guitar with gold strings. Well, that actually wouldn't work. First of all, the strings would break really easily because gold is not that strong. But moreover, you can't really turn gold into a magnet, and so essentially your pickups would not pick up any signal. Okay, and so there's more. So what you actually pick up with your guitar pickups really depends on the motion of the string, not the sound that you make, but the motion of the string. So this is now related to where we actually find these harmonics on the guitar, right? Because if you look at this diagram here, depending on where you put these pickups, you will actually be at the node points of some of these harmonic, and therefore you will not be able to pick up all the harmonics for some of these pickups. And so you see that the further back your pickup is, the more you actually pick up of all the harmonics as your pickup goes further to the neck. This is similar to this to what we talked about before, these different playing styles. You'll actually find that changing the pickup that you use will also change the sound that you use. And so I can actually show that too. So right now, I'm essentially putting this switch all the way in this position. Let's see if you can see it. All the way, I can switch this switch here. With the switch in this position, I'm essentially using this pickup here. If I put the switch all the way in that position, I'm using the pickup right here, okay? So if I put it here, it should sound more like soft and sweet, as if I'm actually plucking over the fretboard. And if I put it all the way here, you should hear it much more sharper than otherwise, right? And so here, if you play, I should actually make sure there's no distortion. This is kind of fairly soft sound. It's not quite tuned, but right, so you get whereas if I put the switch all the way down, you get more this sharp. Right, and that's again, different pickups essentially pick up different harmonics, and so that actually changes your sound. So for some of these, for some songs, what you really want to do is you want to have like a specific sound, or for some funky things, it's easier to have, or better to have that sort of sound. Maybe I have an example for that. that sounds good with the switch in that position. Sounds a lot worse with the switch in the other position. And with that, I think that's all that I have to say. So put your best physics in your rock and keep on rolling, as I would say, and always follow your passion. I think, as you see, that's something that I've always done as well. And since there will not be a live session next week, I already want to make sure that wish you good luck with your exams and your further career. And I'm sure that's on behalf of Dr. Wong and Dr. Tabeishin as well. And I hope you enjoyed this.